Hello friends, and welcome to a lecture on chemical engineering thermodynamics. Today we'll do something interesting. We'll take up a problem which has been asked in Mumbai University Chemical Engineering Thermodynamics 1 paper. The problem is on your screen. It was asked in November 2019 and the problem is 2A. Before I begin with solving the problem, please like and subscribe my channel. This is very important to me. It keeps me motivated to work for you. And please do write in your comments that you would like to have the entire paper or all the problems in the paper in Mumbai University to be solved and put up as a series of lectures. If I receive enough comments, I will definitely be doing it. Okay, now let's take up this problem. An ideal gas is undergoing a series of 3 operations. The gas is heated at constant volume from 300 Kelvin and 1 bar to a pressure of 2 bar. It is expanded in a reversible adiabatic process to a pressure of 1 bar. It is cooled at constant pressure of 1 bar and 300 Kelvin. Well, since it's the third process, this should not be off. It is cooled to a constant pressure of 1 bar and 300 Kelvin. Determine the heat and work effects for each step. Now remember here, and remember this always, whenever you have a problem involving cycles, always try to calculate the temperature at each and every state. Now it's easy to do this if you draw a PV diagram and represent the entire process. So this is the pressure axis, which is bar, and this is the volume axis. Since we do not know the volume, we will take the volume units as meter cube per kmol. So our basis is going to be 1 kilomole of an ideal gas. Fine. So to start with, we draw the isotherm and it's 300 Kelvin and 1 bar pressure. So this is the starting point of your cycle. Now from here it is heated up to 2 bar. Now adiabatically it is expanded to 1 bar. So this can be state number 1, this is state number 2, and this is state number 3. And the last process is getting it back from state number 3 to state number 1. Now we need to know the temperatures at point 2 and point 3. If this is done, the problem solution is very simple and straightforward. Even though we have to calculate the heat and work, we can calculate it by using the change in enthalpy and the change in internal energy. We should know that the Cp is 29.3. So let's start with solving the problem. Let's write Cp as 29.3. So we have Cv as 29.3 minus 8.314, and that gives us 29.3 minus 8.314, and this gives us 20.986 kilojoule per kmol Kelvin. And let's look at, yes, so this is also kilojoule per kmol Kelvin. So we take R as 8.314, which we have already used it. Since there is an adiabatic process, it would be advisable to calculate gamma, which is nothing but Cp by Cv, which in this case is going to be 29.3 divided by 20.986. So 29.3 divided by 20.986, that gives us 1.396. 1.396, we can take it as 1.4. So we have the values, the constants which we want. Now, process number 1 to 2 is a constant volume process. So for the constant volume process, we can write P1 by T1 is equal to P2 by T2. And therefore we get T2 as 600 Kelvin, because the pressure doubles and so does the temperature in the same ratio. Now we need to calculate what is T3. Now T3, you have to remember one thing, is the end of an adiabatic process. Now from 2 to 3, which is an adiabatic process, for this process we can write P2 V2 raised to gamma is equal to P3 V3 raised to gamma. Now we need not know the volumes. People jump to calculate the volumes. No, don't do it. Look at what I am doing. P2, replace V2 by the ideal gas law, that is R T2 by P2, the whole raised to gamma is equal to P3 R T3 upon P3, the whole raised to gamma. That's all. So we have R and R cancelling off. And let's solve it. Remember, I prefer not to simplify things because we have modern day calculators which are very powerful and they can do a lot of number crunching. It is better to use the calculator rather than do a simplification. So what was P2? P2 was 2 bar into T2 was 600 Kelvin, the whole raised to 1.4 divided by 2 raised to 1.4 is equal to P3 is 1 bar into T3 is something which I do not know. It's raised to gamma and this is 1 raised to gamma, which is nothing but 1.4. So we write the value of gamma here, 1.4, 1.4, and we get T3 raised to 1.4. Now let's calculate the LHS, which is fairly straightforward if you try to do it on a calculator. 2 multiplied by 600, the whole raised to 1.4. This is equal to so much divided by 2, the whole raised to 1.4. And that makes it 5874.8901. So that makes it T3 raised to gamma is equal to 5874.89, and therefore we get T3 as 5874.89, the whole raised to, start the bracket, 1 divided by 1.4. So we get the final answer where T3 is 492.2 Kelvin. That's it. We are done. Now this problem can be solved by drawing a table. We draw a table. In this table, the first column is that for the process, the second column is for delta U, the third column is for delta H, the fourth column is for Q and the fifth column is for W. So this is the process 1 to 2, delta U, delta H, Q, W, and all our units are in kilojoules. So let's start with a calculation. Now delta U 1 to 2, since it's a constant volume process, it's going to be 1 kilomole into 20 point, that is the value of CV, where you have the value of CV as 20.986. 20.986 into 600 minus 300. Just to refresh your formulas, delta U for an ideal gas is equal to 1 into CV into T2 minus T1. So that's going to be equal to 1 into 20.986 into 300, and that's 6295.8. 6295.8. So let's make a note of it. 6295.8. Now delta H12 will be equal to 1 into Cp into T2 minus T1. We already have the result for delta U, which is 1 into Cv into T2 minus T1. So we take that 6295.8 divided by 20.986 and multiplied by 29.3 to avoid a lot of calculation steps. So delta H12 is now going to be equal to divided by 20.986 multiplied by 29.3, and that makes it 8790 kilojoules. So that makes it 8790 kilojoules. Now since this is a constant volume process, delta U will be equal to Q, that is 6295.8, and W will be equal to 0. Now process 2-3. Since it's an adiabatic process, the heat is going to be 0 and the delta U is going to be equal to 1 into 20.986 into the final temperature, that is 492.3 minus 600. So that is 1 into 20.986 into 492.3 minus 600. So that makes it minus 107.7. Minus 107.7. Further, that makes it 2260.19. My bad. Minus 2260.19 minus 2260.19. And of course, the delta H is calculated the same way. So that's equal to minus 2260.19. So delta H is minus 2260.19 divided by 20.986 into 29.3. So 2260.19 divided by 20.986 multiplied by 29.3, and that's minus 3155.6, minus 3155.6 kilojoules. So that's minus 3155.6 kilojoules. Now we apply the first law to process 2-3. So yes, a correction here. This was for process 2-3. This was for process 2-3. And for process 2-3, if we apply the first law on it, we get delta U 2-3 is equal to Q plus W. Since Q is 0, it's an adiabatic process. Therefore, we have delta U is equal to W. And therefore, we have the work as minus 2260.19. Now, finally, it is process 3-1. Now, this process is a constant pressure process. So, we take up process 2-3. This is 1 kilomole into 20.986 into 300 is the final temperature minus 492.2 was the starting temperature for the process, and this will be equal to 1 into 20.986 into, start the bracket, 300 minus 492.2. So that's minus 4033.51 kilojoules. So we make a note of it, minus 4033.51 kilojoules. And we use the same old method to calculate delta H. So delta H will be equal to minus 4033.51 divided by 20.986 multiplied by 29.3. So we do it here. 4033.51 divided by 20.986 multiplied by 29.3, and that makes it equal to 5631.46 is equal to minus 5631.46. So we make a note of it, minus 5631.46. Now, since this is a constant pressure process, the heat will be equal to the delta H. So that is minus 5631.46. Now we apply the first law on the constant pressure process. So applying the first law, we get delta U 2-3 is equal to delta H 2-3, since Q is equal to delta H for a constant pressure process plus W. Therefore, W is going to be equal to minus 4033.51 minus of minus 5631.46. 31.46. That will be equal to, let's calculate it out, 4033.51 minus, start the bracket, 5631.46 close the bracket, and we get 1597.95 1597.95 kilojoules. So we get it as 1597.95 kilojoules. Now, before we end this problem, we should make a thorough check. We should check that the summation of delta U and the summation of delta H is equal to 0. If this is confirmed, then we are sure of all our calculations, because for a cyclic process, delta U is equal to 0 and delta H is equal to 0. Now, it's a good idea to do this calculation so as to ensure that we have put the correct results. We have done the correct calculation. So let's go ahead and do it. So we have 6295.8 minus 2260.19 minus 4033.51. Now we get a very small error of 2.1. That is because we have rounded off the decimals, and this error is insignificant as compared to the values of delta U that you have put in. Now let's do the calculation for delta H. 8790 minus 3155.6 minus 5631.46. As you can see, the order of error is same. It's 2.94 and here it was 2.91. So that's about it. And also, always, it is a good idea also to calculate out what is the summation of heat and the summation of work. For a cyclic process, we should have summation of Q should be equal to summation of W. Now let's check that. 6295.8 minus 5631.46. So that makes it 664.34. 664.34. Now let's check the work side. So the work is minus 2260.19, 2260.19 plus 1597.95. So that makes it minus 662.24. So that makes it minus 662.24. Now remember, the error is 2 point some decimal places, and that error is constant. That is because we have rounded off the decimals and done the calculations. Had we taken the decimals exactly to 4 decimal places, we would have got accurate figures. So that was all about the problem that had come in Mumbai University, November 2019. And hope you understood how we can solve this problem in a simple yet methodical manner and get the answers which are accurate and for which you will get a full credit. That was all, guys. Bye. Have a great time.